Hi, I'm Rob Rutenbar. I'm a professor in the Department of Computer Science at the University of Illinois at Urbana-Champaign, and happy to welcome you to my class, VLSI CAD, Logic to Layout. So this is the very first lecture in this course, and so this is basically the introduction and the big picture lecture. What are we doing? What do the course logistics look like? What's the organization of the course at a high level? What's the grading for the course going to look like? And then a little bit of a riff on just, what's interesting in the VLSI CAD business. What sorts of things are we going to focus on? We're going to focus on the design of tools, software, algorithms, data structures to design really big, really interesting chips from a sort of a computer science kind of a perspective. So let's start talking about that.
Welcome to Lecture 1. This is the introduction and overview to our new class, VLSI CAD, Logic to Layout. So let's talk about what are we about in this class? What are we doing? Well, the basic idea is we're trying to figure out how we take ideas for complicated, large integrated circuits and actually turn them into very large scale integrated circuits. So we're going to study the CAD tools. And in particular, what we're going to look at in this class is actually how we design these tools themselves. So we're not quite so much interested in just running existing commercial tools, although we've actually got some open source tools that we're going to let you use running in the Coursera ecosystem. But we're really looking more at the computer science sort of viewpoint here, the algorithms and the data structures and the ideas for how we actually can design these very interesting objects. So here's the class logistics. It's 10 weeks long. There are 8 weeks of lectures. And then there's a free week in order to let you do homework assignments and such. And then there's also 1 week for the final exam. There'll be videos every week in short segments, approximately 2 to 3 hours in total for the instructional content of the course. There are going to be 8 problem sets. So these are basically our homework assignments. So since there's 8 weeks of video material, there's going to be 8 assignments. And we'll leave week 9 open for you to finish this stuff. There's also 4 programming assignments where you're going to write either some conventional, program in whatever language you are comfortable with, C, C++, Java, Python, whatever you like. But also some scripts that we're going to run through some CAD tools that we actually have running on our server so that you can see what they do and you can use those things in some of the homework assignments. So let me talk for a second about grading in the class, and in particular about our 2 badge options. So there's basically 2 paths through the class. So as shown on the left, one path will get you an achievement badge. So there are 8 problem sets, and those will be worth 75% of the credit. Those are single submission. Late submission will be allowed after the deadline for 50% of the credit, and there'll also be a final exam worth 25% of the points in the class, also single submission. And the idea is that you should be doing this path if you just don't have time to do all of the code. And as we look on the right-hand side of the slide, we see that there's actually another way through this class. But this will get you a mastery badge. So you also do the 8 problem sets, which are now worth 40% of the credit. But now there are 4 program assignments, which are also worth 40%. Multiple submissions are okay here. Late submission also allowed for 50% of the credit. Basically, every other week, there'll be a programming assignment that lets you actually write some code or some CAD scripts that we'll actually run out in the Coursera cloud to explore some of these ideas that we're developing in the class. And then there's a final exam that'll be worth 20%, also single submission. And the idea here is that you should be doing this if what you really want is the deepest understanding of the course. Now, some other important stuff, obviously the honor code. It's great, it's good, it's desirable to talk with and work with other people in the class. We certainly encourage that. But what you submit really has to be your own work for the homework, for the code, for any other assignments. And please don't post solutions to any of the assignments on the Coursera site, or share these solutions face-to-face, or share them in email or via the web or with other people. It really just messes up the experience of the learning for the course for everybody else in the class. But please do use the Coursera interaction mechanisms, because Coursera supports some great discussion forums to let you ask questions. And we're going to make use of all of these things to help you connect to us and also to connect to each other. Let's talk for a second about what background you need to be able to do this class. Well, you need some computer science background. You have to be able to write a program, say 500 to 1,000 or so lines in a modern language, and you need to know some basic data structures. So how do linked lists work? How do trees work? How does recursion work? Things like that. In computer engineering, you need some hardware skills. You need to know how basic digital design works, gates, flip-flops, Boolean algebra, Carnot maps to simplify the logical structure of something. And you need to know about combinational and sequential design, finite state machines and such. On the math side, you need to know a little bit of discrete math. You need to know what a set is. You need to know what a function is. You need to be comfortable when I write careful notation to describe some math. A little graph theory is nice, but not really essential. I'll develop whatever you need. We're actually in a few places going to use a few calculus skills. So you need to know how derivatives work, maybe some basic integrals, a little bit of linear algebra as well. The basic undergraduate kind of scientific or engineering math will do it. Basic VLSI knowledge is nice, especially if you've done a little bit of chip layout. That's a nice thing, but it's really not essential. The class is really constructed to be entirely self-contained. If you're watching the video lectures, you're going to learn what we need you to learn about VLSI CAD. So back to the top here, what's the class all about? It's computer-aided design for semi-custom ASICs. So ASIC is an important word for us. It's an application-specific integrated circuit. It's a circuit designed to do a single function. And semi-custom means that we're going to try to design this using some already designed parts. We'll talk about that on the next slide. And the CAD, the computer-aided design, is the flow through a sequence of design steps and software tools. So our sort of universe is described in this diagram. We're going to assume you start with some digital high-level description in some high-level description language. That could be Verilog or VHDL. And that's going to turn into something that you can actually put through logic synthesis, which is going to optimize the gates and wires to actually make it do logically the right thing. That's going to turn into millions and millions of gates and millions of wires. And we're going to put that in an appropriate set of layout synthesis tools, and that's going to actually arrange these things on the surface of the chip, put the wires down, connect them, help us optimize the timing, and so on. And there's a large set of library sorts of things that are supporting this across all of these levels. What we're primarily focusing on in this class is the central objects are basically the gates and wires. So logic synthesis starts with some sort of a Boolean description, gives us gates and wires. Layout synthesis takes gates and wires and arranges them appropriately. Here's a couple of useful acronyms that you're going to see and some terms. Semi-custom ASIC. I mentioned this on the previous slide. An application-specific integrated circuit is an ASIC. That's when you design a chip for a specific task using mostly semi-custom techniques. So if you're designing a processor, that's not an ASIC. But if you're designing something that does, video playback or something with particular sound or, something with cryptography, those are ASICs. You don't really expect to make zillions of them, so you cannot afford to do the opposite of semi-custom design, which is what's called full custom design. They're not quite as dense. They don't have as many transistors per unit area. They're not quite as fast as a full custom design. If we were to look at the differences between the semi-custom design and a full custom design, what I'd say is that semi-custom designs start mostly from pre-existing parts. So we assume you have, a library full of gates that you know how to implement. We assume you have access to libraries of memory so you can put big blocks of RAM down. And we're primarily interested in how we synthesize to those things and arrange those things geometrically to make our design. Full custom designs are really what we say when one does a design right down at the individual transistor level. And honestly, today, microprocessors are about the only things that are really full custom. And there's actually, a couple of other interesting, kinds of things that we could mention. For something, for something like an ASIC today, in US dollars, we're talking about something like, 25 million to do something like that. And, we're probably talking about something like, 25 to 50 people to actually design that sort of thing. But if we were talking about something like a full custom design, gosh, we're talking about something like $100 million, maybe let's say 100 or so people, maybe a couple of hundred people. Is really complicated, expensive teams to do those kinds of designs. And even today, the full custom processor designs, they have huge amounts of semi-custom parts on them. So we're focusing on semi-custom ASICs in this class. One more really important acronym that I got to get you. CAD is computer-aided design, and that's what we all used to call this world of tools for chip design. And the problem is that a lot of our friends also do CAD. So our mechanical engineering friends who are designing cars, they do CAD. Our architecture friends who are designing bridges, they do CAD. CAD's not very specific. So what people who really do chips tend to call it is EDA, electronic design automation. That's what most insider chip folks call it. It's a more accurate and a more descriptive name. The problem is that people outside the business are not always clear what this means. So I chose to call this class VLSI CAD because I wanted it to be easily understood by people who are interested in this, but it's really honestly VLSI EDA. So if you want to sound smart to somebody who does chip design, call it EDA. Now you know. One more important acronym to talk about is SoC, System on a Chip. A system on a chip integrates lots of blocks of function on one big chip, and most commonly what we do is we take blocks and implement functions, and we use things called standard cells, which are basically gates or flip-flops. We arrange these things in rows, we connect them with lots of layers of wires, we intersperse these things with big blocks of memory like static RAMs, SRAMs, and then inside these blocks we can implement anything we like. So we could implement some random logic, we could implement some sort of a CPU core, we could implement some arithmetic function, we can do anything we want, and we mix and match these sorts of blocks to make a big system on a chip. They really look like that. This is a very simple one. And I've just got some of the blocks, called out. There are a bunch of, as we can see here, there are a bunch of big memory blocks on the surface of this chip. There's a big blob of random control logic that's actually talking to a bus. There's another little tiny processor. I think it's only a 4 or an 8-bit processor implemented as rows of gates over there on the side. And this is an interesting chip. This is a controller chip. It's actually got an analog interface that talks to some strange voltages out in the industrial world, but it's still a nice little example of a system on a chip. Another important term from this class is a flow. How do you attack big designs like this? Well, the big idea is levels of abstraction. You break the problem down into smaller steps, and every step renders the design a little more real. So the synthesis steps, those are the ones that go down, right? So that's synthesis, right? Those are the ones that go forward in the design. They take the stuff from the last step and they make it a little more real. And the verification steps, those are the ones that look backward. Those are the ones that look back up. Okay, those are the verification steps. They check that it actually worked. And a complete set of steps is called a flow. And flows can have many hundreds of steps in a real industrial design. But for our class, we're going to have a really simple flow. Right, so we're going to basically look at things in these sort of 4 areas. We're going to look at logic synthesis, and that's going to start with some Boolean logic sort of design description in a kind of an abstract form, and it's going to get us real gates and wires that are optimized in some reasonable way. And we're going to look at a little bit of logic verification. We're going to primarily look at some ways of telling if your design is correct in some very simple ways in the Boolean domain, in the gates and wires universe. And then the gates and wires go into a layout synthesis set of tools that actually arrange them on the surface of the chip, which is just a big rectangle, and decide X, Y coordinates for all of those things. And they're also going to look just a little bit at timing in this universe, so we can try to figure out something about how long things actually take in a fairly simple way. Now, I have to say that this is a tremendously oversimplified flow. But in the kind of 10 weeks that we have available to us, I think we can actually cover this. So the big goals for this class are to explain the critical algorithms and the critical data structures and the modeling assumptions that are used in each of these big steps. So let's go start and see what some of those things are.